Okie doke. So in the last few lectures, we've looked at, the last two lectures, we've looked at the sort of fundamental building blocks of the standard model, how to construct it out of principles like the gauge principle or gauge symmetries, and choices of representations of fields under those gauge symmetries. And then we build up this quantum field theory, which is the standard model. And I hope at this point you have at least a qualitative understanding or feeling for those aspects of quantum field theories, because they will be useful throughout, even if it isn't a quantitative picture. If you don't feel confident that you could sit down and calculate something, some scattering amplitude in some, with corresponding to some Feynman diagram or something like that, that isn't so much of a problem, because the goal of this lecture course is really to try and give you more of a sort of a feeling for the foundations and structural aspects. The next, in my mind, the next most important thing to think about is that now that we have constructed the standard model, we've not in the way it was historically constructed, but it's the same theory, and we've constructed it out of choosing some gauge symmetries for no reason other than the fact that we know that they are a good choice, and then choosing some representations of fields, be they fermions or vectors or a single scalar doublet, which is the Higgs doublet, and then seeing what we got. And we looked at the various different interactions that we can get, or operators that we can get at different dimensions. And then briefly touched upon this notion of relevance of operators, thinking about the ones that are most important at low energy. So the ones that will be most important, for instance, if we're doing collisions at the LHC. Finally noting that at present, we don't have any evidence for the existence of operators at higher dimension, although we believe that at some energy scale they will show up and become relevant, because the standard model itself is not, we say, UV complete, which means it can't be a fundamental theory. So the next step is to really continue studying the structural aspects of the standard model. And I think the best way to do that is to now take a little bit of a harder look at the symmetries of the standard model. We've discussed symmetries, U1 symmetries, non-abelian symmetries, and so on. And the reason I think that that's the appropriate next step is that, in my view, and I think many people share this view, symmetries are really the most immediate way of getting at understanding some physical phenomenon. In the early days of field theory, when people were studying Maxwell's equations, it wasn't so clear what the symmetry structure was going on there, but actually hidden behind all of those equations was essentially a U1 symmetry and essentially Lorentz symmetry as well. And with our understanding of symmetries, we gain in my view, a deeper and more fundamental understanding of the physics that's going on. And also pragmatically, symmetries can sometimes enable us to calculate certain things exactly that wouldn't have been calculable otherwise, so certain physical phenomena perhaps, or even postulated phenomena in a hypothetical theory. Or they can give us a quantitative understanding of how certain properties behave, even when we can't calculate exactly. And this is very useful, for instance, in the days of QCD, where we had only the energies to access things like pions and various different mesons, kaons, and things like this. And understanding the approximate symmetries of the standard model in that context enabled many very beautiful calculations to be performed that give a good estimate of various physical predictions, even though QCD itself, is a very difficult theory to calculate, and one would really ideally need like large-scale supercomputer lattice calculations to actually calculate these things exactly. So it's a very, very useful tool. And it turns out that the standard model is chock-a-block with all sorts of interesting approximate symmetries. And this can help to understand various structural aspects of the standard model and various phenomena that we see in nature. By approximate symmetries, what do I mean? Because symmetries sort of seem like a binary thing or not. You can do that U1 rotation or you can't, right? It sounds like it's something that should be an on-off switch. But that's not really the case, because if in your theory at some energy scale, imagine you're working at LHC energy scales, if in your theory there's a parameter which is small that happens to break an asymmetry, then to a good approximation, the theory behaves like it has that symmetry, even though there is some small parameter that breaks it. And also, if there's only some small parameter that breaks it, then that can help us estimate, even without doing exact calculations, even forgetting about factors of 2 or -1s, we can estimate the magnitude of various different physical phenomena by understanding that if some phenomenon requires some symmetry breaking, then it must be proportional to that small parameter. So it's a super, super useful tool. And there are different types of approximate symmetries in the standard model, different sort of classes in my mind. I've tried to classify them as best I can. The first sort of class of symmetries that I want to discuss are accidental symmetries. So what do I mean by an accidental symmetry? We will come back to this, and we will see. When I go through this, we will see it in more. But an accidental symmetry is really a symmetry that nobody put there by hand, but it just sort of turns up in the lowest dimension operators, so the operators that are most relevant, by accident. So, for instance, we will see in the standard model that just by dint of the gauge symmetries and the representations, the low dimension operators, like the operators at dimension 4, just so happen to have some, we'll go through them, some symmetries in them, because thanks to the gauge symmetries, there's no operator you could write down, no interaction you could write down that actually violates those symmetries. So we say it's accidental because it may be present in the low dimension operators, even if at high dimensions, which means sort of higher energies, that symmetry is not present at all. So we call that an accidental symmetry. And there's the two that I want to discuss in the standard model have a lot of relevance to nature and even to potentially to our existence. So the first is to consider a symmetry where we take a quark. I'll call some fermion that is a quark, this little q here. And we, as always, as we keep doing, we rotate it by some phase. I'm calling it theta q goes to q. And all of the QCs, remember in the standard model, we had the DC and the UC. These are the sort of, we call them sometimes the right-handed or conjugate pairs of the quarks without a C. If they rotate in the opposite way, then we can potentially have a symmetry. So we've got a plus I here and a minus I here, theta q, QC. And we can postulate a similar one. So I would call this sort of like a Barial number symmetry, because this is just operating on the quarks, which carry Barial number. And similarly for the leptons, one could have a symmetry I call it theta L. That looks like a C. Theta L rotating the leptons, and LC rotates it going to e to the minus I theta L rotating the leptons times L. Okay, so this top symmetry here, we haven't fixed the normalization yet. Theta q is just any old theta q. We would call this Barial number symmetry because it's acting on the quarks, which carry a Barial number. And this theta L, again with some unfixed normalization at present, is rotating the leptons. So we would call that lepton number symmetry. So this is something that would rotate all of the quarks the same way. Here, quarks this way and anti-quarks this way, but no discrimination between, for instance, an up quark or a top quark or a charm quark. And here, similarly, this would rotate, for instance, the electrons, muons, tau, leptons, but also the neutrinos. Okay, now we can choose the normalizations and the rotations in any way we wish. This is a potential symmetry, and we're going to play with it and see what it implies. And we can also do rotations that do a rotation at the same time. So we could pick one, for instance, that does a theta q rotation that happens to be equal to theta lepton, or happens to be equal to 3 times theta lepton, or something like this. So we can split them up any way we wish. Now this is going to seem totally ad hoc at the start, but you will see at the end of this lecture why I'm splitting them up this way. So we can call it Barial number symmetry and lepton number symmetry, or equivalently we could call it B plus L symmetry and B minus L symmetry. And for these symmetries, we simply have that theta L would be equal to, let's call it theta, and theta q would be equal to 3 theta. So we rotate theta L by the leptons by an amount proportional to theta, phase proportional to theta, of an angle theta. and at the same time do the quarks by 3 times that. Or another possible option would be that theta L goes like minus theta plus beta B minus L. So the leptons are rotating in the opposite way, and theta Q would be equal to 3 theta. Because we can essentially, out of these two symmetries, we can pick any 2 linear combinations. It's like just like rotating a 2-dimensional vector. So long as you have a vector space that's 2-dimensional, you can write it in any way you want, so long as you have 2 linearly independent combinations. It turns out it's the same for these U1 symmetries. Okay, so now we go on and consider the standard model. And as before, I'm going to write down, well, you've got them in your notes or the last lecture or the online notes that I have provided. The lowest dimension operators in the standard model, we can keep going up. And it turns out that if we write the standard model as these old pieces, L0, that was like the cosmological constant, L1, that was 0, plus L2. That was just the Higgs mass, plus L3, that was 0, plus L4. And we stop there, so we don't do L5 and beyond at the moment. So I'll put a red cross through this. So if we stop at L4, then it turns out that, and you can do this, you can see this just in the equations themselves, that both of these symmetries are exact symmetries of these operators. Now, we did not impose these symmetries a priori. We did not require that the theory must respect these symmetries. In fact, just as a result of the gauge symmetries that we did impose and the representations that we chose, it just so happens that up to dimension 4, it's just impossible to write something down that actually violates these symmetries. And that's why we call it accidental, because we haven't imposed them and they've just sort of emerged in the lower dimension operators, which we would say is emerged in the IR. IR just means low energy. Hence the lowest dimension operators is emerged in the IR by accident. And actually it's a sort of, it's a widely held view for many reasons that global symmetries like this, non-gauge symmetries, should actually be accidental, that actually theories that involve, for example, quantum gravity, don't truly respect or care for global symmetry. So if one emerges at low energies, like for example these two, then you could only really expect it to be as the result of some accident like this, where the gauge symmetries alone are enough to forbid interactions that violate those symmetries at low energies. Okay, so now let's go back to L5. So let me rub that out and include L5 and beyond. And we find that at dimension 5, there is indeed already a higher dimension operator that we studied yesterday, which violates U1 lepton number. You see, this is L dot H squared. H does not transform, the Higgs does not transform under these B plus L or B minus L symmetries, but L does. So you can see that this violates lepton number. So it breaks these two symmetries down to one linear combination, which is preserved, which is Barial number. And this is super duper important. It's telling us that although when we write down the standard model, it looks like leptons and quarks are sort of on an equal footing, in reality they're not. That's sort of an illusion that really follows from the fact that we're only writing down the lowest dimension operators. And so once we conceive that there's more to life in those lower dimension operators, that there is additional physics in the UV, which means high energies, short distance scales, then we would expect it to generate interactions like this, unless there's some extra symmetries around that forbid it. And so this is a super duper important operator. And in fact, as I said, it really starts to separate the leptons from the quarks once we go to higher dimensions. The fact that this operator can exist. Sorry, that shouldn't be squared. That should just have one power of mass dimension in the denominator. And indeed, there is a corner of the standard model in which quarks and leptons do look completely different. You know, if you look at the up-type quarks and their mass ratios, they look sort of similar to the down-type quarks and their mass ratios. Of course, there are practical differences. The bottom mass is not identically equal to the top mass and things like this. But there are these sorts of hierarchies of, you know, a couple of orders of magnitude or an order of magnitude as you go down the generations. But it's sort of reflected the same between the up-type quarks and the down-type quarks. However, when we look at the lepton sector, something totally different is going on, because the charged leptons have a mass hierarchies that look qualitatively similar to those that we see in the quark sector. Yet neutrinos are an entirely different beast. The neutrinos are super duper light. You know, the sum of their masses is less than, you know, 1 electron volt or something. So if you think about it, that's, you know, 11-ish orders of magnitude lower than the weak scale. Furthermore, it appears that their mass splittings that we can measure, the neutrino mass splittings, we can measure from neutrino oscillations, either neutrinos that have come from the sun, solar neutrinos, and atmospheric neutrinos, and also you can measure the neutrino oscillations using neutrinos produced in nuclear reactors. And their mass splittings don't seem to follow that sort of a pattern at all. In fact, when you do global fit the data, you still can't tell what the mass hierarchy is and so on, but they don't seem to have these exponential hierarchies the way they do in the quark sector or in the charged lepton sector. So there is something different going on in the lepton sector than is going on in the quark sector. And right enough, when you go beyond dimension 5, you see that within even the standard model itself, it does not treat leptons and quarks in the same way necessarily. Furthermore, this is the interaction, this particular interaction can generate neutrino masses, because essentially in L dot H has a vacuum expectation value that we will come to, which generates all of the particle masses. And L dot H looks like a Majorana mass for neutrinos. That's what is generated from this once the Higgs obtains its vacuum expectation value. So there's sort of strong hints, this is all circumstantial, but the approximate symmetries of the standard model, particularly when we look at accidental symmetries, sort of become very, very suggestive that maybe quarks and leptons aren't quite on the same footing. You know, lepton number symmetry is not on the same footing as baryon number symmetry. Baryon number symmetry seems to be preserved to higher dimension operators beyond dimension 5, whereas lepton number not so. Okay, again, I'm trying to give you a qualitative structural perspective on these things. If you wish, you can calculate, for instance, the neutrino masses coming from this operator. And this operator is something that's generated if you want to know what sort of microscopic physics. You notice I use microscopic, short distance, high energy, and UV interchangeably. All these things, they're all when I say them at least, they all mean essentially the same thing. There could be different microscopic physics, which is actually responsible for this. And the best game in town, and it has been for 4 decades, is the so-called seesaw mechanism, which automatically generates this sort of interaction by integrating out heavier states that we know of as right-handed neutrinos. Okay, so let's go beyond. So at higher dimensions, this lepton number could be broken. What about B plus L and B minus L at lower dimensions? We've seen that there's no operator that we can write down, so the Lagrangian is actually invariant. However, in terms of symmetries, when we work with the quantum field theory, and I alluded to this yesterday, in terms of symmetries, one has to be a little bit more careful than just checking that a Lagrangian is invariant under symmetry. In fact, to really claim symmetry, to have a quantum conserved current, one must really ensure that the path integral itself is invariant under any symmetry. And the question I want to ask is that the case for, actually I'm going to stay on this side of the board, is that the case for B plus L and B minus L? And as I'm sure you can guess by the way I chose to speak about B plus L and B minus L rather than B and L, that there must be some discrimination between these two things. So let's recall we're working with a quantum field theory, so it's not so much, you know, if we think in terms of the path integral, it's not so much the Lagrangian that has to be invariant, but it's the Lagrangian, also the entire path integral. if only the Lagrangian is invariant, that you would say that you have a classical symmetry, but it's not respected at the quantum level. And the path integral, as I sort of mentioned yesterday, alongside mentioning that I'm terrible at these curly Ds, these are the fields. We call this piece here the path integral measure, but it's just that bit that integrates over all of the different fluctuations the field could have when it's going from the A to B. You know, the field value at different space-time points could fluctuate in different ways. And then e to the I over h bar times the integral over volume integral over the Lagrangian. So, as I've claimed, for B plus L and B minus L, this guy here is actually invariant. Nothing changes when you perform that symmetry operation. So only if you restrict to dimension 4 and below. So it is a classical symmetry, is how we would phrase it. However, and also, so this is the path integral measure. Now, one can look at this in a number of ways. I'm not going to go into it because it's way beyond the technical level of these lectures. But one can calculate using a method that's really the best way of doing it. You can draw triangles that you may have recognized. They're known as triangle diagrams. So you would have some diagram that inserts some symmetry current operator here, and then a triangle of fermions, and then, for instance, 2 gauge bosons. Things like this. You can calculate Feynman triangle diagrams, which was sort of pioneered, I think, mostly by Adler, Jacques and Bell. And Jacques and Bell were actually here at CERN. That's Bell, you may know of, recognized from Bell's inequalities in quantum mechanics. Also, Bell pioneered work on a non-perturbative breaking of symmetries. So you can calculate them like that. But I think the nicest way to do it, to see it, is that you can use this method developed by Fujikawa, which showed how to determine if this piece here is not invariant under some symmetry transformation. In any case, you do that and you perform a symmetry transformation, and it just so turns out that this path integral changes. And after you do the full calculation, the new path integral, after performing a B plus L transformation, changes from being this to the same sort of thing with the same silly curly D and phi, e to the I over h bar, then the old Lagrangian, because the old Lagrangian never changed, put this in brackets, plus now an extra piece, which includes the electroweight gauge coupling squared, theta 32 pi squared, WA mu nu, WA mu nu, this guy with a tilde. And I'll come back to explain what this term is. I hope you can read it okay. But the basic take-home point is this is not equal to this. The path integral changes when you perform a B plus L transformation. When you perform a B minus L transformation, it just so happens that you do get contributions like that, but they cancel each other between the quarks and the leptons. So if you were to do a B transformation, you'd have a problem. If you did an L transformation, you'd have a problem. But if you do B minus L, it remains, those contributions cancel. So the whole path integral remains the same. But B plus L, it doesn't. And what this means then is that the full theory is not invariant under a B plus L transformation. And so we say that even though the Lagrangian is, and so we say that this symmetry is broken quantum mechanically, or we say that there's an anomaly, or we say that it's broken non-perturbatively, because there's no this effect is not something that is just sort of related to some specific order in perturbation theory. You can see it, through those triangle diagrams. You can see it using perturbative techniques. But it turns out that it's actually, if you just use that perturbation theory at lowest order, that one loop triangle diagram, that gives you the entire correction. And you can see that by studying the change in the path integral. Now, these effects are small, which sort of makes this sort of an accidental symmetry of the standard model, even though if you work at dimension 4, this symmetry breaking is present. And the reason is that the effects are pretty small because they typically scale like exponentials. if you have something like this and you have some higher dimension operators, for instance, that break Barial number or lepton number, then the effects that you will get, because this transformation involves B plus L, the effects that you will get will scale something like, I can't remember the exact numbers, but typically like something like 4 pi over h bar alpha a week. You see there's a factor of 4 pi and alpha week here. And so if alpha week is a small number, if your theory is perturbative, so g squared is small, then this is e to the minus 1 over a small number, so it's e to the minus a big number, and e to the minus a big number is exponentially small. So the effects of this breaking are pretty small, and for all practical purposes, for most practical purposes, you never need to worry about them. But nonetheless, you should know that they are there. And indeed, there are effects like this that you may hear about if you're doing some collider physics relating to electroweak ailerons. It's the same sort of physics that's coming in here. Furthermore, there's an aspect that this could be relevant for, which is the fact that we exist. So the standard model in itself does not contain enough of the right ingredients to generate an asymmetry between matter and antimatter. So really the universe, if we just had the standard model on its own, and it started off at some high temperature, we wouldn't be around. There would be such a small asymmetry between matter and antimatter that there'd be hardly any matter left in the universe. And so we have this puzzle, we call it the matter-antimatter asymmetry, and we need to figure it out. And it turns out that these sorts of effects could play a role in explaining that. They couldn't explain the whole thing, because we definitely need to change certain aspects of the theory. The way the electric phase transition proceeded needs to be changed, and potentially also the amount of CP violation, which we'll come to in a second, would need to be changed. But nonetheless, these processes that scale like this, that are related to this very fact, could help understand the origin of the matter in the universe, and hence all of us. Okay, so those were accidental symmetries. I'm sorry if conceptually I'm going quite fast. I'm not really doing any calculations, but these are some pretty heavy weight conceptual aspects in the standard model and quantum field theory. But my approach is that I believe you're all capable of handling these conceptual aspects, so why not discuss them? And also because I think sometimes it's good to have some discussion of these things to reflect on, in your future careers in particle physics. You're likely, if you interact with theorists for sure, you're likely to hear these sorts of statements over and over again. Okay, so now let's go to, those were accidental symmetries, and let's go to some of the approximate symmetries. Actually, I'll just leave that title up because that already had approximate in the title. So to consider the approximate symmetries, let's consider just the electrons, right? The fairly mundane particle. So I'm going to work in terms of the Weyl spinners. I'll come back to that. You will hear, and it's very, very infuriating in some sense, the way textbooks swap, different textbooks use different notations. There's sort of 3 ways of dealing with spinners. There's Dirac spinners, Majorana spinners, and Weyl spinners. I'll discuss that in a second. But let me work in terms of the Weyl spinners. So in terms of the Weyl spinners, we have EC and L, that's the first generation of leptons. So this guy contains sort of like the neutrino and the left-handed electron. And we can write the standard model Lagrangian terms that involve these guys. And we will have the usual kinetic terms, EC dagger, D slash EC plus I L dagger, D slash L. Plus then the Yukawa interaction with the Higgs, which is ultimately the thing that gives them mass of the electrons, H dot L EC. And this is the Yukawa interaction here, plus summation conjugate. All right. So what do I mean by Weyl spinners? So I'll just do this in blue over on this side quickly, and then we can carry on with the physics. So Weyl spinors have two components. So it's called chi1 and chi2, where these are complex numbers, and they're Grassmannian complex numbers. Dirac spinors, so this is a Weyl spinor, and this is the smallest object you can have that forms a spin half representation of the Lorentz group, which is why I like to work with it. I like to work with the smallest objects I can because I'm not smart enough to handle bigger objects. And so I like to work with Weyl spinors. Dirac spinors are spinors called psi, which are made up of a pair of Weyl spinors. So you'd have something like chi, a Weyl spinor, but then also some other one I'll call phi c, which is also a Weyl spinor. So this has four components. And we sometimes switch between these things. So we could write, for instance, if we had a Lagrangian in terms of two Weyl spinors, and here you'll see that there's a sort of a symmetry. D slash, I've got no gauge interactions, the sort of dumbest thing you can imagine. Phi c dagger D slash phi c plus m chi dot phi c plus summation conjugate. This is the two kinetic terms for the two Weyl spinors, chi and phi c, and a mass term with respect to U1 symmetry. So I can rotate this guy by e to the I theta and this guy by e to the minus I theta. This is respected, this respected, and this respected. So we've got a mass term that respects U1 symmetry. But I can equally well write this guy in terms of Dirac spinors as something like I psi bar d slash psi plus m psi bar psi. But I have to find some convention for this d slash to now involve four-dimensional Dirac matrices, whereas these d slashes used a two-component, two by two Pauli matrices. It's all the same story, but it's different notation. Finally, you could, if you wish, write, imagine you had a single Weyl spinor with a mass which breaks the U1 symmetry. So write something like plus m over 2 chi squared. Then you can equivalently define a Majorana spinor, where you have the Weyl fermion here and its own self conjugated essentially, and form a mass term that we normally would refer to as a Majorana mass term. So all of these things are interchangeable. I apologize that we have not settled on the same convention between all of us theorists or anybody else who writes textbooks. We just have to live with it. Okay, so now let's go back to the approximate symmetries. So here we see that we could rotate e to the I, rotate this guy EC by some constant rotation. EC goes to e to the I theta EC. And also L, let's call it theta E, and L goes to e to the I theta L. If this term doesn't exist, then we can separately perform these two different rotations, and the theory has a symmetry. So the symmetry has two U1 symmetries. But if the electron Yukawa does exist, and this coupling to the Higgs is there, then we see that we can only perform this rotation if theta E is equal to minus theta L. So what that tells us is, and we call these two symmetries chiral symmetries because they're rotating a Weyl fermion on its own. And so we see that we have two at the level of the kinetic terms, we have two U1 symmetries, but at the level of the Yukawa interaction, we actually only have one. So clearly, YE explicitly breaks one of the U1 symmetries. So we start off with two, but then in the presence of YE, we just have one where theta E is equal to minus theta L. So YE is this Yukawa interaction is a parameter that explicitly breaks a global symmetry. And so we now have a tool by which we can understand how YE can enter into processes if those processes involve breaking of the chiral symmetry. Furthermore, YE is a tiny number. You know, YE is something like the electron is the mass. You can write it in terms of the mass of the electron divided by the vacuum expectation value of the Higgs, which you will get to. And it's something like 3 times 10 to the minus 6, which is a very, very small number. So what this means is, imagine we're scattering electrons at super high energies, like 100 GeV or something like this, way, way above their mass. Then it's a very, very good approximation to basically ignore this and pretend like in all of your scattering processes that your electrons have this additional chiral symmetry where you can rotate them by independent phases. To all intents and purposes, all of the measurements you can make will behave like that's the case, because the electron chiral symmetry breaking is just such a small parameter. It's a very good approximate symmetry at high energies. However, if we go to lower and lower energies, for example, energies around the mass scale of the electron, then at those sort of scattering energies, this amount of chiral symmetry breaking, which comes essentially from this Yukawa and the fact that it generates an electron mass, is comparable to the energies and energy scales in the process. So at low energies, you'll have to take full account of the electron mass in all of your scattering experiments. And so you see that this is very, very, very useful organizational principle. If you're doing, building, as we hope to do here at CERN, an E plus E minus Higgs factory that will operate at 240 GeV and will produce Z bosons and W bosons, and for me, most importantly, a load of Higgs bosons, millions of Higgs bosons. If we do that, then for most of our calculations, it's actually a really good approximation to just forget about the existence of this Yukawa term at all, because it's very, very unimportant, even though it's a relevant operator, even though it exists at low energies. Okay, so that's one example of an approximate symmetry and how it's useful, but there are many other approximate symmetries. We see them, for example, in the quark sector as well. As the first generation quarks are very, very light, and so there's an approximate symmetry there that we will return to when we come to discuss pions. Okay, and so for the last part of this lecture, I want to discuss some space-time symmetries that are also we should have time to get through this. Some space-time symmetries that are also very relevant, and in a sense they are like, well, to a greater or lesser degree, a form of approximate symmetries of the standard, form of approximate symmetry of the standard model. Okay, so let's discuss Cp and T. Okay, so I've really been discussing what we would normally refer to as internal symmetries, so symmetries where you rotate some field in the theory by some constant phase, some description, or be that a non-abelian rotation or just an abelian rotation. But space and time have not really come into the discussion yet. But it turns out that in addition to Lorentz symmetry, boosts and rotations, it's possible that nature also respects some discrete symmetries. And indeed, it's a theorem that in any Lorentz invariant quantum field theory, there's one discrete symmetry which is known as Cpt, which is always preserved. However, that does not mean that the sub-symmetries themselves have to be preserved. So you could, for instance, violate T, and that would then imply by the Cpt theorem some violation of Cp. Or you could violate, for instance, just P and not C, and things like this. And these are also, these symmetries are a useful sort of organizational tool by which to understand some physical effects, particularly physical effects that violate parity or Cp can have profound experimental signatures, really radical experimental signatures. So what are these symmetries? So they're really as dumb as you might think. So parity takes, a vector, and not a pseudo vector, but a vector, and flips the spatial components. So T and X goes to T if this were the space-time vector, for instance, t and minus x. The t operator does the same thing, but for time. So t and x goes to minus t and x. And charge conjugation acts in a sort of similar way, but I'm going to give you an example, show you how it can act on a gauge field by just using the Cpt theorem. So let's take a gauge field. So a mu, this is a four-dimensional gauge potential, I guess we'd call it, that we may write as a0, the time-like component, and a underscore, which is like the spatial vector in the x, y, and z direction. So we perform a p transformation. We get this, a0 and minus a. So it's called a p transformation. If we perform then a t transformation, we get the top bit flipped signs, we get minus a0 and minus a. It didn't do anything to this component. So we see that PT has just completely flipped the sign of the gauge field. But CPT is invariant, so CPT is a symmetry, so C must act on the gauge field as flipping the sign of the whole thing. So we get A0 and then A back again. We get back to where we started to, which is just here. Okay. So these are how the symmetries act on gauge fields. One other way of looking at it would be, and this is probably where C for charge conjugation comes from, is if you were to flip the signs of all the charges of the fields in, for example, under U1 hypercharge. Okay, so now the question we want to ask is the standard model CP invariant? And it turns out that no, it's not necessarily the case. It didn't have to be, but there's something fishy going on. So consider, for instance, this combination here. It might be an interesting homework exercise to do this calculation explicitly. So take the fully antisymmetric four-dimensional tensor, epsilon mu nu alpha beta. And so this has, its entries are zeros when any of these guys are the same, and ones, and then when you flip signs, you get minus ones. So you can construct this yourself. Now, if we contract this with the field strength tensor, which we met before, remember this is doing f alpha beta, but in terms of the vector field, that would be d alpha a beta minus d beta a alpha. If we contract these two together, we get something that we call f tilde mu nu. And f tilde means that it's CP odd. So under CP, this guy, no, let me, sorry, I shouldn't say that yet. Okay. When we do this, we see that the combination, I'll just write down the full Lagrangian that we can have. I'm going to put in, just for the sake of normalization, which is useful for me, but it's not really important for the physics, the gauge couplings. So I'll do G prime for the hypercharged gauge couplings, and then some unknown parameter theta y over 32 pi squared f mu nu f tilde mu nu. That's in the hypercharged sector, plus then the weak sector theta weak over 32 pi squared W alpha mu nu W tilde A mu nu, plus potentially in the strong sector as well, G strong squared theta strong 32 pi squared G A mu nu G tilde A mu nu. And F is the field strength that goes like d mu A nu minus d nu A mu, where A is the hypercharge gauge field. It's the same sort of thing here for the electroweak gauge fields, where now this is the same combination. almost up to some extra interaction term that we'll come across later. And now there's all of the different gauge fields. So for the SU2 theory, there's 3 gauge fields you have to sum over here, and that's what these A's are. And for QCD, there are 8 gauge fields you have to sum over. And it turns out you can do this for homework. I wouldn't bother doing it for these guys, but you could do it for these guys. You can show that this combination here, when you do a CP transformation, is odd, so it flips sign. And what that means is that nature could have chosen to have terms like this. These are dimension 4 operators. And nature could have chosen them for them to exist. And if so, if they did exist and these theta y parameters, and these are just unknown parameters that we could maybe go and measure, if these parameters were non-zero, this would tell you that nature likes to violate CP in the gauge sectors. And the reason for that is that this is non-zero and I do the CP transformation. This guy flips sign, this thing remains the same. So the whole thing is flipped sign, so you don't get the same Lagrangian that you started with, which means it's no longer, it's definitely not a symmetry. So this is one way in which nature could have violated CP. What's really peculiar is what goes on here. This thing here, it turns out, so all of these are what we call, all of these operators are what we call total derivative operators. So they don't actually, if you do any perturbative scattering process, and you include these operators, so you send in some, for instance, gluons from infinity and scatter them and see what happens, you will never get an effect proportional to these guys. It's like they live these interactions. When we say they're a total derivative, you might remember things like Gauss's theorem and stuff like this, where if you have the integral over total divergence, that's the same as evaluating your integral on the surface of the volume that's enclosing it. And so these operators, sort of, in some respect, they live on the surface and they're total derivatives, so you shouldn't expect them to be important. However, when we include these non-perturbative corrections that I discussed before, they turn out to be that they can be important. This one here for QED, no, doesn't happen, which is basically to do with the fact that QED is quite a simple gauge group. It's a U1 symmetry, and well, I'm just going to divert a little bit because it's just super interesting, but you don't need to know this. But basically, if you take a sphere at infinity and you evaluate these things on the sphere, then there's no interesting gauge configurations because U1 is like a circle. And if you draw any circle on the sphere, you can always shrink it to 0 size. And that essentially is because of that reason that this is unimportant. That's not the case here. If you have something that involves SU2 factors, this is SU2 and this is SU3, and SU2 is a subgroup of SU3. If you have something with SU2 factors, you can actually find gauge field configurations that you can wrap around the sphere, which cannot be shrunk away to nothing. And so they actually do contribute. However, the effects from this guy are exactly like the scaling that I showed you before, this e to the minus something, 4 pi over alpha weak factor. And when alpha weak is small, which it is, these are exponentially suppressed and unimportant. You get the same effects in here. And however, the strong gauge decoupling actually at the QCD scale is not a small number. So e to the minus 4 pi over alpha strong is not a small number. And it turns out that these could be very important. But for some reason, we've, experimental physicists have performed lots of measurements of the effects that this could give. And the main one is a neutron electric dipole moment, and it's not there. So there's something very, very fishy going on. That's why I started this by saying something fishy, something we don't quite understand about what's going on with CP violation in the gauge sector. And it's a completely open puzzle. Nature didn't have to respect CP in the strong sector. And it turns out that for some reason it does, even though, as we will now see, it does not respect CP in the quark sector, which is intimately linked to the QCD sector itself. Okay, so just to finish up, I want now to discuss CP violation and quarks. Okie doke. So let me write down again the relevant interactions for the quarks and leptons. So we have the sum over all of the flavors of, for example, the Q quarks, dagger D slash Q, I do J, sum over J, plus I, U dagger C, D slash U, J, C, plus I, D, J dagger, D slash, D, J, C. And then we also have the Yukawa interactions, which can be off diagonal. So you could couple, for example, an up quark to a charm quark and things like this. So Y, I, J, U, H, Q, J, Q, I, sorry, U, J, C, plus Y, I, J, D. So this is for the up quarks Yukawas and the down quark Yukawas. H dagger, Q, I, D, J, C. Okay, so the kinetic terms, because they're all the same, and you can bring them to be all the same by a field transformation. So even if we didn't start off with them being the same, we could make them all the same. These kinetic terms are diagonal. You see that they treat each guy as you sum over the first Q's, then the second Q's, and the third Q's. Similarly here for the UCs, up, charm, top, all treated in the same way. And so these terms actually respect the unitary transformation, which is that the Q's, the three Q's, three generations can be rotated by some unitary matrix UQ. The D's, C's can be rotated by some unitary matrix UD, DC. And the UCs by some unitary matrix UC. So when we do this, because these are unitary matrices, U dagger U just gives you 1. So all of these terms remain the same. But then we can actually use this to diagonalize these matrices. So I can choose, this is just some 3 by 3 matrix. So I can always choose a unitary matrix on the left and a unitary matrix on the right to make this thing a diagonal and just the 3 eigenvalues down the center. So I can do that, and I can completely diagonalize this Yukawa interaction if I wish. But I can't do this one. And the reason is I don't have enough freedom yet, because I've used up my Q rotation and my DC rotation to bring this guy into a diagonal form. But here, I've already used up Q, so I can't do what I want here, and all I can use is my DC transformation, sorry, my U. Here I use my Q and my UC, and here I have no longer Q to U, so I cannot bring this into fully diagonal form. And in fact, the best by rescaling fields, rephasing fields, and everything, the best I can do is to bring this YIJD matrix, 3 by 3 matrix, into a form which involves a IJ. Unitary matrix, the CKM matrix, multiplied by some diagonal matrix, which I'll call YD, big Y, capital YD. So this guy here is diagonal. And actually has real eigenvalues. And this is a 3 by 3 unitary matrix. And it cannot be rotated away. And that means it's physical. We can do nothing to remove it from the theory. There's off-diagonal terms in there. And furthermore, this CKM matrix has some freedoms in it. So it's a completely general 3 by 3 matrix, but it's not, which would normally be parameterized by 8 parameters, which are the coefficients of the 3 generators. Sorry, the 8 generators for SU3. Recall we did discuss that a little bit in the first lecture. But we can actually do a little bit more. So there aren't 8 bits of parametric freedom in there. We can do a little bit more by rephasing the fields, and ultimately, the UCKM, the Kabibu-Kobayashi-Muskawa matrix, UCKM, has 3 mixing angles in it and 1 complex phase. And under a Cp transformation, this phase, let's call it delta. Do we call it theta? Let's call it delta. This phase delta goes to minus delta. So if the value of this parameter is non-zero, then the full standard model cannot be invariant under Cp, because if we keep delta fixed under Cp transformation, then something changes in the theory, because the only way for it to have been respecting Cp would be if delta had gone to minus delta. And indeed, this has been observed in the quark sector. Sorry, that's my dog. This has been observed in the quark sector, where essentially through kaon oscillations, through kaons oscillating into anti-kaons, so very beautiful measurements, have discovered a Cp violation in the quark sector. Okay, so this CKM phase, it enters in a very specific way through the quark sector, and that helps us understand where the quark sector Cp violation feeds into certain observables, certain things that we can measure. And indeed, it's been measured in the quark sector through essentially kaon oscillations as the first place, but now it's been established in a few different ways. And it turns out there's actually a very similar story that goes through in the lepton sector as well, through largely, though not quite identical, sorts of arguments. Okay, so let's leave that today. So that was our discussion of approximate and accidental symmetries in the standard model. Again, sort of building a structural intuition for how the standard model works and what to expect of it. And in the next lecture, we will finally go into some more nuts and bolts about what's going on in the electroweak sector and the Higgs sector, and in particular, how spontaneous symmetry breaking in the Higgs sector generates particle masses and so on. And I'll leave it there.